My name is Jaya Muleman, and with the help of my mentors, Dr. Victoria Roundtree, Dr. John Seeger, and Dr. Fred Adler, I have conducted research on the effects of underwater noise on whale group dynamics. Whales rely on hearing to assess the world around them, communicate, avoid predators, and find mates, because even in clear water, visibility is seldom greater than 100 or 200 feet. Underwater noise levels are affected by many factors, including weather. Wind stirs the surface of the water, creating waves. Crashing waves create bubbles, and when those bubbles pop, they create underwater noise. Underwater sounds travel 4 times faster, affecting a larger area than the same sound would in air. This noise competes with whale communication. Masking occurs when a sound in the same frequency band as another makes the second sound inaudible or uninterpretable. The upcall is believed to be the primary contact call of southern right whales. The upcall sounds like this. The upcall is in the frequency range of 50 to 200 hertz, as you can see in the graph on the left. One study found that wind generates a frequency of 100 hertz to 5,000 hertz, and another found that it generates a frequency of 100 hertz to 1,000 hertz. Both of these studies support a frequency overlap from 100 hertz to 200 hertz with the upcall. This range composes 2/3 of the upcall's frequency, indicating that it is a possibility that underwater noise due to wind is masking southern right whale upcalls. The data for the study spans 10 years from 1987 to 1996. I investigated group dynamics in the southern right whale population that lives off the coast of Peninsula Valdez, Argentina. Peninsula Valdez is a calving ground. It has gulfs with slowly sloping beaches, which provide the perfect conditions for mothers to protect their calves. The mothers concentrate in shallow water near the coast so that predators can only come from offshore. This photo shows 6 whales close to shore at Peninsula Valdez. The ripples at the surface and the arrows mark their location. Scientists survey whales from a plane flying around the upper Gulf, which is Gulf of San Jose. You can see that right here. The outer coast, and the lower Gulf, Gulf of Nuevo, right here. These areas are where most whales are seen. The scientists then place whales into groups based on proximity. The study assumes that the number of whales in a group is an accurate measure of whale proximity. Calves were subtracted from group size number because their behavior is the same as their mothers. Adults are defined as in a group if there is at least one other adult in the area. This study uses wind speed to represent underwater noise. Wind speed data was downloaded from NOAA's ERDAP server, which gives estimates of surface wind speed every 6 hours. Exploratory analyses using different statistical tests comparing group size to an average wind speed over 24 hours before an aerial survey showed that there was a significant relationship between underwater noise, as represented by wind speed, and whale group size. Later, we realized that group size is not the best response variable because we're really interested in the behavior of individual whales. Groups are a consequence of the choices made by individuals. So in our final analyses, we looked at the probability of an individual adult being in a group versus being alone, and we asked whether that probability varies with wind speed shortly before an aerial survey. For these analyses, we used a binomial logistic regression, which models the probability an adult is in a group as a function of wind speed. So what is the effect of underwater noise caused by wind on whale grouping behavior? Whales may have 3 different possible responses to an increase in underwater noise. One possibility is that whales form larger groups as noise increases. Therefore, whale distribution may be more compact on days following rough weather. Peninsula Valdez is a calving ground, which means that the population is mostly comprised of mothers, calves, and juveniles. Grouping increases vigilance and thus animal survival. When whales are in large groups, there are many ears listening for danger, which allows them to detect small changes in their environment. Since hearing is a whale's primary method of sensing their environment, an increase in underwater noise can make them more vulnerable to predators such as orcas. Mothers might then stay closer together to alert each other to predators over the loud background noise and thereby protect their calves. A second possibility is that whales become farther apart in the presence of noise because they cannot hear each other. Mother and calf pairs tend to stay around 10 whale lengths apart in the regions where they concentrate, perhaps to reduce calf play and thus reduce energy expenditure when the mothers are fasting. Mothers use the upcall to communicate with others in the area. When noise increases underwater, calls to neighboring mothers may be obscured. A louder ocean may cause whales to spread even farther apart because of their inability to hear one another. A third possibility is that whales do not respond to noise induced by wind. My research investigates all of these possibilities. These graphs show the distribution of the two data sets compared in this study. As you can see, neither is normally distributed. The most frequent number of whales seen in an area is 1, and the most whales seen together is 33. The wind speed graph shows an average wind speed over 24 hours before an aerial survey. The low is 7.5 kilometers an hour, and the high is 36.8 kilometers per hour. To begin, we performed a simple linear regression on the data, even though the data is not normally distributed. This was to see if there was any sign of a trend. Even with this naive model, we found that as wind speed increased, group size increased. This was significant with a p-value of 0.0004. This relationship prompted further testing. After exploratory analyses using many different statistical tests all showed the same relationship, we realized something. We are concerned with individual whale behavior, not group behavior. This led us to look at the most appropriate test to answer our question, a binomial logistic regression. Here is the result of the binomial logistic regression. This graph shows the effective wind speed at different lengths of time from the start of the aerial survey on whales joining a group. The height of the bar tells us the size of the effect of wind speed at that time on whale grouping, and the color tells us how statistically significant that relationship is. For example, the darkest blue bar tells us that the wind speed 12 hours before a survey has an effect size of 0.05. This tells us that for every kilometer per hour increase in wind speed, there is about a 5% greater probability of a whale being in a group. This relationship is significant with a p-value of 1.06 times 10 to the negative 9th. This graph tells us that the effect of wind speed on grouping decreases with time, with two exceptions: 12 hours before the survey and 36 hours before the survey. 12 hours before the survey has the largest effect on if a whale chooses to be in a group. What makes this really interesting is that the wind speed 36 hours before actually makes the whales less likely to join a group. This relationship has a significant p-value of 0.0001. This study found that there is a significant relationship between increased underwater noise caused by wind and whales forming groups. This may be because underwater noise reduces the ability for mothers to work together and alert each other to the presence of predators. If they get closer together, they may be able to hear each other better over the background noise and protect their calves from danger. It makes sense that the longer before the survey, the less wind speed affected whale grouping. The exceptions are 12 hours before the survey, which is 9 p.m. the night before the survey, and 36 hours before the survey, which is 9 p.m. 2 nights before the survey. 9 p.m. the night before had the largest effect on whales choosing to form a group. This may be because human variables reduced the effects of 3 a.m. and 9 a.m. on the day of the aerial survey. It is possible and not unlikely for there to be high wind speeds the night before at 9 p.m., but the wind calms down enough by the next day to do an aerial survey in a plane. If there are high winds at 3 a.m. and 9 a.m. on the day of the aerial survey, it might not calm down enough to take the plane out and survey the whales. It is very interesting that 9 p.m. 2 days before had a negative effect on whale grouping. Maybe it's because it makes wind the next night seem like less of a big deal, or maybe it's because if they expended energy the night before to form a group due to high winds, they're less likely to expend energy the next night to move into a group. We don't know. I will be continuing this research this summer when I hope to further investigate this question. In conclusion, this research has shown that there is a significant relationship between increased underwater noise and whale grouping. This research has also shown that underwater noise 12 hours before the survey has the largest effect on whale grouping. This study gives us an insight into individual whale behavior, their strategies for survival, and response to environments where noise makes communication difficult. A ginormous heartfelt thank you to Professors Victoria Roundtree, John Seeger, and Fred Adler for your never-ending patience. Thank you for always making time to answer my questions, get excited about whales and new ideas, and for lending your invaluable knowledge to this project. Thank you to Luciano, Sylvia, Andy, and Aaron who facilitated the Ecology and Legacy minor. This gave me the opportunity to go to Peninsula Valdez, discover research, and fall in love with the southern right whale population I would later do this project on. That's me in the photo whale watching at Peninsula Valdez. And lastly, thank you to UROP for supporting students in research.